Okay, so last time we met, we looked at a snapshot build of FS2. Today, I'm going to work with the brand new 090 milestone 2. And so there were some API changes from milestone 1 to milestone 2, but as of milestone 2, I think the core API is going to be very stable. And last time we looked at a bunch of things. We looked at working with pure streams. We created those with like the apply method on the stream constructor. We were able to do things like treat them as collections and eventually convert them to collections. And then we also looked at effectful streams. And specifically, we looked at the task data type from FS2. And we saw how we could evaluate tasks or evaluate effects in the construction of streams, either to build up the elements of the stream or to affect something like writing to a file or writing to a network as we're processing the elements of a stream. And then at the end, we looked a little bit at pipes and how to write our own pipes and combinators on streams. So today we're going to look at pipes in quite a bit of depth. But before we do, I do want to address one bit of errata from last week. And that's the task.apply method. Last week we did this example of printing the current thread name. I remember when we first tried to use task.apply, we got this error about needing a strategy in scope. And so we created this thread pool of 4 threads and then executed this task here. And what we expected to see was that when we ran it, we should have seen the print line being executed on a thread from the thread pool, and we didn't. It turns out that was, in fact, a bug in FS2. And that has been fixed in 090 milestone 2. Okay, before we dive right into pipes, I want to take a look at one of the core data types that FS2 uses internally. So it's not quite at the surface API, although it is pretty close, and that's the chunk data type. So if you recall from last week, we opened a file and we read all the bytes from a file. So we had something like a source, which was a stream of task, byte. And if we were to look at the, if we were to think of a stream as just like a collection, then it's probably not efficient to have like all of these individual bytes put into this big stream data type, specifically because of boxing and unboxing of those bytes. Additionally, there's a lot of things happening with FS2 internally as we try to evaluate and run these streams in a way that is stack safe. And if we were only to ever operate on like a single byte at a time, we'd lose a lot of performance trying to work with very large streams. So one of the big departures of, or in FS2 from the previous design from Scala Z Stream is that internally, the elements of a stream are always chunked into groups. So a chunk in FS2 is just a strict collection, right? It's a collection of elements. It's finite, and we can read from it. It's completely immutable. So you can see this chunk data type is parameterized by a type A, and we've got a pretty primitive set of immutable collection methods. Things like we can take the size, we can uncons an element, right? So we can get basically a head and a tail. Now, if it's empty, we'll get back a none, but if it's non-empty, we'll get back a sum, which is made up of our head and tail. And then we can do things like efficient lookup by index, drop and take and fold and so on. And so if you looked carefully at the output last week, when we were doing things like stream 1, 2, 3, we had these descriptions of the stream we were building get printed as the toString of our streams. And you can see these chunks kind of hanging out in here. And so internally, there's this chunk structure where we move around these groups or these like little mini collections of elements through the stream pipeline. But typically with the surface API of the library, we're only going to be working with a single element at a time. So when we said, for instance, stream123.map and just add one element, if we looked at the description of it, you can see that we still have this initial stream, chunk 123, and we've got like this deferred mapping operation that when we evaluate this stream, we're going to call this map chunks function, passing, some function 1 to it. But the interesting thing here is that, like map, we're working with an individual element basis. But when we evaluate the stream and actually run it, our function is going to be applied to the individual chunks. And the way we can see that is by using the chunks method on stream. So if we use the chunks method on stream, what it does is says, for every chunk that's flowing through the internal stream pipeline, when we hit the chunk, let's just lift that up to like an individual element level. So to give you an idea, if we were to convert the stream 123 to the list of its underlying chunks, we'll see that there's only a single chunk inside of it, the one we started with, 123. If we were to do something like append stream 4, 5, and 6 onto 123 and then run that same conversion, you'll see that we see each of those two chunks separately because of this chunks combinator. Whereas without the chunks combinator, we're not aware of any of this chunkiness of our source data, right? Without the chunks combinator, it just feels like we're working with individual elements. But internally, we really have kind of batched them up into these chunks. So I want to take advantage of this and show an example with using take. So if we did the stream 1, 2, 3, and we called repeat. And so remember what repeat does is says emit all of the elements from the stream, and when we get to the end, go back to the beginning and emit the stream again, and just keep doing that forever. So we're going to turn this stream 1, 2, 3 into an infinite stream of the numbers 1, 2, 3, right? And so if we were to say, let's take the first 10 elements of that and convert it to a list, we get the flat list 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. But what if we were to take the chunks? So we take the 10 elements, but then we say, show us the chunk structure. Lift those chunks up to the stream level. And you can see what's happening is that we're getting our chunk 1, 2, 3. The initial one is the first chunk, and then it hits the end of the stream and repeats. And so we get another full chunk of 1, 2, 3. A third full chunk of 1, 2, 3. And then finally, for the 10th element, we get a truncated version of our 1, 2, 3 chunk. So what's interesting about this take function is that it's preserving the chunkiness of our source, right? So the source is always going to be emitting these chunks of 3 elements, and take is not breaking that down. It's not like re-emitting chunks of a single element. And that's really important if we want to preserve the performance benefits of this chunkiness, right? If FS2 only supported chunkiness in the creation of sources, but then all of the various methods that let us operate on sources on these streams, didn't preserve that chunkiness, then we would have, we would throw away most of the point in chunking and lose all the performance benefits. Okay, so let's take a look at MyTake. So here's the definition of MyTake, which we wrote last time. And so let's just run through this real quick. So MyTake was a function. We passed the number of elements to take. And we said that this was going to return a pipe that may evaluate effects of type F, has input of type A, and has output of type A. And recall, the definition of pipe is just an alias for a function 1, a function from stream FI to stream FO. So the way we implemented MyTake, we wrote a little helper function here in this Go, which we'll look at in a second. But the function 1's right here. We say, give us the input stream as a closure, as an anonymous function. And then we're going to pull elements from that input stream using our helper function Go. And then our helper function Go is just recursively defined. It says, it tracks its own remaining element count that it needs to take. And says if that's less than or equal to 0, then we're done. And if it's if it's not, we're going to receive a single element from the stream we're pulling from. That's going to give us the step value, and we're going to pattern match on the step value and say, give us that single element we received, and give us a handle to the remainder in our stream that we're pulling from. And then what we did is we said, output a single element of what we received, and then call ourselves recursively, saying we want to take one less element. We pass the remainder h, right, to our Go function recursively, so we pull from what's left. So this is how we defined MyTake. Oops. So what happens if we use MyTake with our definition of stream here? So let's try to do it. So instead of calling take 10, we want to call MyTake 10. Now we don't have any syntax, right? Our MyTake def here is a pipe. It's defined as a function, just standalone function. So I can't just call it directly on stream. And so last week we called it using the through method on stream, which said, feed the elements of this stream through this pipe, or let this pipe pull elements from this source. Now this isn't quite going to work. And unfortunately, we've run up against a limitation in type inference here. Our stream123.repeat has type stream of nothing, comma int, because we have no effects, right? We're still working with a pure stream here. And Scala C doesn't like to infer nothing for various reasons. And so really what this big screen of red is telling us is that it can't solve for F here. Like you're calling through and you're passing a pipe, and the pipe's parameterized by some type F, but Scala C really doesn't want to infer F equals nothing. And you can see it does tell us that somewhere in this big wall of output, right? It says that it found a pipe where the F type was nothing, but it needs a pipe with some unbound F type, just some arbitrary F. And so, of course, you could stick nothing into this arbitrary F to make this compile, but Scala C won't infer that. So we could either, apply some type parameters up here explicitly to make this example compile, or we could just use the through pure method. So through pure exists solely to work around these types of inference issues. And you only ever need to use through pure if you're working with a pure stream over here on the left. If you have an effectful stream, you don't have to worry about through pure. Okay, so that compiled and it ran, but notice what happened. Our output now, we have 10 chunks where every chunk just has a single element in it. And so last week I said that when we went to define MyTake, we were going to do it in sort of the most straightforward way. And in some sense, it's the most naive way to do it, right? That it's very straightforward to define it that way, but we give up this chunkiness preserving property. So really, the question becomes, how can we rewrite MyTake such that we preserve the chunkiness like the built-in take function had? So let's look at MyTake. So we're going to define a new function called MyTakeC. Just where C is short for chunkiness. The signature of the function is going to be the same. We're not going to change anything about the signature. It's still a pipe that receives elements of A and outputs elements of A. And we're not going to define, or we're not going to change the basic structure much either. The overall structure is still going to be defined as an anonymous function here that pulls on the stream using a recursively defined helper function go. What is going to be a little different is that instead of receiving a single element from our stream via receive1, we're going to receive a chunk of elements from our stream all at once using h.receive. Now h.receive, just like receive1, returns a step. So our pattern match still works here. But now instead of getting back an individual element A, we're getting back a chunk of A's. Okay? Now, since we're getting back a chunk of elements, we don't know, is it okay? We don't want to output all of that entire chunk each time because we don't know if that chunk has more elements than we're supposed to be taking. So really the body here inside the pattern match is that we want to check if the chunk size is more than the number of elements remaining to take. So if chunk size is less than or equal to the number remaining, then we can just output this chunk in its entirety and then call ourselves recursively, just decrementing the remainder by the size of the chunk. And we can do that with pull.output instead of pull.output1. Right, so pull.output takes a chunk as an argument, and we have that chunk right here. So then we'll call ourselves recursively through this bind, right, through this monadic composition operator. And we're going to say go, and now we want to say not n-1, but rather n- chunk.size. And then we still pass the remainder. Like this remainder h is not really the tail, it's the remainder after this chunk. Right? So that part doesn't really change. Now we need to handle the case where we have, let's say, a chunk of 5 elements, but we only have 3 elements left to take. So if we go back to the definition of chunk, you can see it's a pretty small API, right? Chunk does not extend anything, and there's something like, let's say, 20 methods. But chunk defines take. So over here, we can just say pull.output chunk.take n. Right? So if the chunk has 5 elements and we're only supposed to take 3 more elements, we can just say take 3 from this chunk. This gives us a new chunk back with just 3 elements. Then we can output that. Now, we don't need to call ourselves recursively here. We're done. Right? At this point, we know that there are no elements left. We've gotten n down to 0. And so we can get rid of the old code and give this a shot. So if we run MyTakeC now through Pure, you can see we've succeeded in preserving the chunkiness of the source. So when we did take 10, we had that same behavior. And in general, all of the built-in methods on stream and the built-in pipes that we'll look at, in general, they all preserve chunkiness of the sources, at least when possible. And this is a big trick to like FS2 performance tuning. If you want to get the most performance out of a stream-based program, you want to give some consideration to the chunkiness of your data. Now, if your programs consist entirely of using these built-in combinators, you may not have to think about this much. But then again, you may, because maybe your data source is providing your elements in chunks of like 1 or 2 or 3 elements, and it would be better computationally to like buffer those into chunks of 100 elements before running through the rest of the stream. And so those types of buffering features and other types of features as it relates to like asynchronous retrieval of source elements into the buffers, there's all sorts of combinators built into the library to help with those types of things. Okay. So I want to look at a little more detail as to what's actually occurring here, and specifically this line. We had this anonymous function. In was a stream, right? Because remember, a pipe of FIO is just a function 1 from stream FI to stream FO. So in is a stream, and we're calling the pull method on a stream, and then what we're passing it is a function from handle to pull. So this particular method, pull, let's take a look at it. Okay, so pull says you pull with this function called using, and using has type handle FA to pull. So pull is really an alias, and it's an alias for a very specific pattern of working with streams. And so I want to kind of back away from the alias for a minute and look at the underlying pattern that it's providing for us. So the general idea is if we're going to pull on a stream, let's do an effectful stream before we get started. So let's say we've got some stream called source, and we'll make it effectful in the task effect. And we'll just make it an infinite stream of 1, 2, 3. And I'm going to lift the pure stream 1, 2, 3, up into the task effect with this covary method. Right? So that's sort of like a type-safe cast. It's saying that if you have a pure stream, you can absolutely treat a pure stream as a effectful stream. All right, so we have this source stream. And what I want to do to this source stream, actually, let's start here. What I want to do to this source stream is open it. So there's this method called open. And what open does is it converts the stream to a pull. We talked about this a little bit last time, but a pull is like this monad that lets us pull elements from wherever the stream is getting its data using methods on handle. And we said that a pull has 3 type parameters. It has the effect type, right? Meaning that in the act of pulling elements, we may want to evaluate effects of this type, right? Or once we've pulled an element, maybe we want to evaluate an effect of this type to do something with it, like writing it to a network or writing it to a file. We had an output type. The type of value that our pull is going to output back into the stream when we eventually use this thing. And we had a resource type or a result type. And we said that, or at least I said last week, that the pull data type is a monad, And specifically, it's a monad in this last parameter. So the result type is the thing that we can like map over, right? So if we took source.open and then called like the map function, what we get here is this handle, right? We get whatever this third type is. Right, so for now we can just make the identity function. But if we were to instead say like convert that handle to, let's say, unit, we've changed this third type from stream.handle to unit. Right, so we have this monad in the third type parameter, and we can do things like Flatmap, of course, since we have a monad. And now what do? Well, since it's Flatmap, and we're calling it on this pull monad, we need to return a pull monad that has the same effect type and has the same output type, but we can vary the element type, or the resource type, or the result type. So for example, we could say, just return pull.done. We've used that pull a few times already. Whoops, typo. Right, so we can say pull.done. And now you can see we still have a pull of task, a slightly more complicated task, but we won't get into that today. We still have this output type of nothing, right? In that we've opened the stream, but we haven't actually tried to output anything yet. So, we have this output type nothing. But now we've changed our result type of the stream.handle to a result type of nothing. So this is kind of an elegant thing, right? Since it's a result type of nothing, that means like if we were to call .map and do something with x, we know at the type system level, we know that this that this particular function will never, ever, ever, ever be called. It cannot be called. And we know that because at this point, the type of this overall expression had the result type of nothing. And there are no values of type nothing, right? Nothing's the bottom type in Scala. There cannot be a value of type nothing. And hence, there's no way that this code could ever execute, because x here, since we're mapping over the overall expression, x has type nothing. So we could put something here, right? We could just map x to unit. That's fine, but we know at runtime that this function's never actually going to be executed. Okay. So that's fine. And actually, let's actually run this. We have an infinite stream, right? So let's just take the first 10 elements of our infinite stream before we open it, just because I don't want to run forever. So then we're going to open it, we'll flat map, and then we're going to call pull.done. So what we have is a pull. So how do we get out of a pull and get back to a stream? We do that by closing it. So when you open a stream, you get a pull. When you close the pull, you get back a stream. Okay? And now if we run this, you can see what we get back is something that has no output. And the types even told us that all along, the output type of our pull was nothing in each of these expressions. And so we knew we were going to get no output. And hence, when we run it, we get back this vector of nothing. That it has to be empty because there's no possible way we can stick a nothing value inside of it. All right, so how do we do something a little more interesting? Instead of running, let's say, pull.done, what if we were to say pull.output the number 42? Sorry, pull.output one element of type. We're going to output a singleton chunk, a chunk of one element, the number 42, and then we're going to be done. Right? So if we just evaluate that, we have a pull, we close the pull to get a stream, We then run the stream, logging all of its elements, and that'll give us a task, and then we evaluate that task at the edge of the universe, and we get back an output of one element. So you can sort of start to see maybe what that pull alias that we looked at earlier, the lowercase pull, the method on stream, does. At least it's likely that it's going to open it. It's going to open the stream that we called on. It's going to call Flatmap. And now, what is this type here? Like, what are we passing to Flatmap? We're passing a function from the result type of our pull to another pull. That's really what this is, right? So this sort of looks like our recursive go function. We can't define it recursively here in line, right? But that's sort of what it looks like, is that we've got this function from a stream handle to another pull. And at the very end, we're closing it to get back to a stream. So if we were to go look at the definition in FS2 of the way that a pull is defined, here's the way pull is defined. And there's a lot of syntax here and a lot of type parameters here to work with variance parameters. But effectively, we have our using function, our function from handle to pull. And then inside of the body, all we're doing is opening the stream, flat mapping on it using our function, and applying the H from Flatmap. And then with the overall expression, we're closing it. So this looks a lot more complicated here in the FS2 source because of all the variance annotations, and we're not working in an OO style here. Everything's just a top-level function. But you can see that like this pull method, which sort of felt like a primitive last week, is really just implemented in terms of open and close in Flatmap. Right? Open on stream and then close in Flatmap on the pull method. Okay. So I want to move on and look at the way another function worked that we looked at last week, and that was interleave. So interleave, we said we have got a stream 1, 2, 3, and we can interleave that stream with a stream 4, 5, 6, and convert the result to a list. And you can see what interleave did is, took an element from the first stream, then took an element from the second stream, right? Then an element from the first, then an element from the second, and so forth. So what is this structure here? Like we've got two streams that we're putting together into a single stream. Right? Like what we got back here was a stream. And so it turns out like that, if we consider our take example again, with take, what we said was like take is a function that's actually implemented using a pipe, where we're taking this source and feeding it through our pipe to generate a new stream. Interleave sort of feels like that, but we've got two streams that we're combining in some way to generate a new stream. And so just like the fact that take was defined as like syntax directly on stream, interleave is defined as syntax on stream. That's really implemented with another primitive, which is pipe 2. So here's pipe 2. So pipe 2 is the 2-argument equivalent of pipe. In the same way that like function 2, right, a function of 2 elements that has 2 input values that has 1 output value, a pipe 2 is one of these like streamy functions, right? A function that says given 2 stream inputs, I'll give you a new stream output. Okay, so we have an extra type parameter. Pipe 2 has the effect type that we're going to potentially evaluate effects in. we have the input type of the first stream, the input type of the second stream, right? And then the output type, or the type of the output stream, I should say. But the neat thing here is that pipe 2 is really just a function 2. So let's look at the way interleave is defined. And actually, let's look here. So here we have this trait in the FS2 source called stream pipe 2 ops, and this is the trait that adds all of the syntax to a stream related to combining two streams into one. And so our interleave method here says, on some stream FO, we can interleave that with another stream of FO to get back a stream of FO. So we can combine like this self stream with the stream S2. And we're going to use that using this interleave pipe 2. So there's this object in FS2 called pipe 2. And if we look at it, it's just a standalone object. And if we look at interleave, we can see interleave here on line 115 is defined as a pipe 2 that just fixes the input, the first and second input types and the output type all of the same value O. And so a pipe 2, remember, is just this type alias that expands out, right? A pipe 2 can be rewritten as stream FO here, stream FO to stream FO in this particular case, right? Because we've set all three type parameters to be the same. And so what does the implementation of this interleave look like? Well, we use this zip pipe 2 defined somewhere else, defined up above, and we're just using like underscore syntax here. And so if we were to get rid of that placeholder syntax, we would say like we've got some input stream I1 and another input stream I2, and we're just going to call zip of I1, I2, and then call Flatmap on the result. Right, so in order to define this pipe 2, we're just defining it as a function 2, as this anonymous function of 2 arguments. So for folks that are familiar with Scala Z stream, pipe 2 takes the place of like T and of Y. So there were these two types, T and Y, in Scala Z stream. They both had this ability to combine two different streams together. And the difference was one of purity. Like T's could combine elements together deterministically, is a better way to put it. Whereas a Y could combine two streams together non-deterministically. So like interleaving two streams is a deterministic option, or a deterministic transformation, right? We have two streams and we're always going to say, take the first element from the first stream. When we get that, now switch, take the next element from the other stream, right? When we get that, switch back. We always have this defined deterministic behavior as we toggle back and forth from our inputs. As opposed to like just like a race, like a merge, where we're just taking two streams and merging them together as fast as there's elements available. There we're basically saying like whoever's got data first, output that data, right? That's a non-deterministic operation. And so in Scala Z stream, those two concepts, deterministic, non-deterministic transforms, had to be encoded very differently. Whereas here, because of the way we've got this pull monad defined, we can do this interleaving just by opening both of our two input streams. Right, and it's a little hard to go through all of the reuse of all of these methods here to show that. But if you were to trace it down, like if you looked at the definition of zip, which is defined up above, And then you see that's implemented with a zip with, and that's eventually implemented up with this zip helper. And, if you eventually traced it all down, you'd see that really all it's doing is opening both streams and then recursively deciding which handle to pull from. We end up with a handle for each stream, and we decide, which one we want to get the next element or chunk of elements from. So I want to do a bunch of examples of this stuff, and I want to do it up at the surface API level rather than implementing our own pull twos. And in order to do these examples, I want to I'm going to use some time-based examples. So Scala Z stream has this time package. There's a bunch of different methods. The one I want to start with is AwakeEvery. So AwakeEvery takes a duration, like a period, and gives us a stream that has an element every period. So this isn't going to compile quite yet, but we could say something like awake every second. In order to do that, we're going to need a couple things. First, we're going to want to import duration syntax. So now we can do things like write 1 second. And the next thing we're going to want to do is provide a scheduler to the AwakeEvery method. We do that implicitly. So we can create a scheduler in the same way that we created a strategy. And so what the scheduler is used for is every time our period elapses, the scheduler is going to handle that time management, wake up and execute some evaluation which will cause our stream to have data in it. So it's worth pointing out that the scheduler is not actually used to evaluate our own effects. So if we were reading from a file or reading from the network and doing so in a blocking way, our effect itself isn't going to run in the thread pool backing this scheduler. Rather, the scheduler is only used to wake up at the appropriate time and then enqueue some work into our strategy. And our strategy is always where all of our actual effects are executed or evaluated. Okay, but we have now our duration syntax, we have our scheduler, we can now call AwakeEvery. And then sort of like the file API, we have to tell AwakeEvery what monad, what effect type do we want it to evaluate in. So we're going to say we want you to evaluate in the task effect. And now what we get back is the stream durations. So let's look at what that means. Let's take the first 5 elements from this stream and log them into a vector, and then let's just run this overall program. So you can see we're hung here. We called UnsafeRun, so we're blocked. We're waiting for these elements to appear. We blocked for 5 seconds. And then after 5 seconds, our take 5 finished. And as a result, we got back this vector. And so you can see that the finite duration we're getting is the number of nanoseconds since this overall stream started evaluating. Had we done the same thing with let's say 250 milliseconds, right? We'll block for only a little over a second, and then you can see the durations are all 250 milliseconds, more or less apart. Okay. So let's say instead of taking 5 elements, we want to run this program for a certain amount of time. And the other thing I want to do is, rather than collecting up all of our output into an output vector, let's log it all as the output is seen, right? As we actually get these elements, let's process it and move on. Let's not collect stuff into memory forever. So if we want to do stuff as elements are seen, we could use map. But now, this is kind of a little dangerous, right? Like if we were just to do print line here, we're sort of in a world where we're mixing pure and impure things, right? Like map should be a pure function that we're, or this function that we're passing to map should not evaluate arbitrary effects. And here we have got this like side effecting print line. So, if it's a quick debug type environment, this is probably fine. But what we really want to do is delimit our effects here. Like maybe what we're trying to do is write this value to a file or to the network or put it into a database, something like that. And in those types of cases, we want to be very explicit about the use of these effects. And so we could do something like task.delay. Right, and capture this, this effect. In this case, we're just printing to the console, but capture this effect in our task monad. But this isn't quite what we want. Whoops. This isn't quite what we want because what we end up with is a stream that evaluates effects of type task and then outputs tasks. Well, so that's not what we want to do. We want to somehow, we don't want to output these tasks. Instead, we want to kind of switch from the value level to the effect level, right? As we get these values of type I, we want to evaluate effects as a result. We don't want to output effect or effects values. So there are a variety of ways to do that, but the simplest way is with the evalMap function. So with evalMap, we can make this transformation. We can move from this value level operation, like here's some value of your output type of your stream, finite duration, into the effect level, like just evaluate it. And now what evalMap is going to do is that says this result type here has to be a task of some x. It can be any x. And then what you get back overall is a stream of task x. So in our case, we're print lining, so our x is going to be unit. And so when we execute this overall, we get back a stream of task unit. But now if we were to say like run this and then call UnsafeRun, this is going to run forever. And we will see values click off as they arrive once a second, but there's nothing to stop this. So one option is that there's this UnsafeRun for method on task. So we can just give it a time limit. We can say only run our program for up to 5 seconds. And if we do that, you can see it clicks off as it gets the elements. And then when it hits our time limit, it throws an exception. It says, hey, this didn't finish within your specified 5-second limit. And that's why we got the timeout exception. Well, this isn't really what we want. UnsafeRun for, first that's at the edge of the program, right? And we don't want to encode these type of limits in, if our program needs these type of like time limits or other type of cancellation logic, those types of things, we don't want to rely on things happening at the edge of the program, nor do we want to encourage people to like pull these unsafe calls up into like the core of our stream logic. We really want to keep those unsafe calls at the very edge, never use them internally, and yet somehow be able to encode this timeout logic into the core of the program without having to worry about the messy world of effects. So this isn't quite the right approach. Instead, what we really want to do is say, like if we take our overall stream, and let's just call this like ticks, right? So we've got the stream called ticks, which when we run it, it's going to run forever, and it's going to just print line the time. So what we kind of want to do is say, like, run the ticks thing, but stop running it when some other condition occurs. And there's a built-in pipe 2 for that. So if we look at the pipe 2 object, there's a bunch of different methods. One of which is interrupt. So we could call pipe 2 with this interrupt method to say, like, run the ticks thing and then interrupt it when something else occurs. Now, just like with take, when we looked at the built-in definition of take, we saw that, you know, we had this pipe.take operation, which was this, you know, pipe here. But then we also had like the s.takeEnd syntax where we had like the OO style version of it. And we see the same thing with interrupt. So if we were to do ticks.interrupt, you can see here it's called interrupt when. And there's two overloads of interrupt when. Both of them, you know, take a single argument, and both of the two overloads, the only argument's name is halt when true. So this first one is the one we're going to use. It says halt when true, and you pass it a stream of booleans. So basically, it's going to, you know, interrupt when is going to say, I'm going to pull elements from, you know, whatever stream you put on the left-hand side of me. And I'm going to continue to do that as long as I haven't seen a true from whatever stream you stick on the right side of me. So maybe I've seen nothing from this stream halt when true. Like there's been no output whatsoever. Or there has been output, but all of the values have been false. So is there something we can do with interrupt when where we can say, like, run our program for 5 seconds? So how could we do that? We want to say, we need a stream that when you open it and you start pulling elements from it, it doesn't have any data in it for 5 seconds. And then after 5 seconds, it has a true. It has a value, you know, true. So that seems maybe challenging. And there's a bunch of different ways to do it. It turns out there's a pretty straightforward way to do it using some specific features of our task data structure. You know, task has this schedule method. And the idea of schedule is you can give it a value and you can give it a delay. And what you get back then is a task that when run won't actually complete synchronously, or won't return a value for this delay. So this is one way to do it. We could say task.schedule, schedule a true for 5 seconds from now. But now, you know, our types aren't quite right. That gives us back a task of Boolean. We need a stream of task Boolean. And so we could just wrap this in a stream.eval to say evaluate this task, you know, when opened or when run. So if we were to now run this program, we'll see it click off for 5 seconds and then it'll stop. And actually it ran for, it looks like about 10 seconds. So there's something interesting there with the schedule and the tasks that's probably worth investigating why it ran so long. Something must be up there. But I don't really want to rely on specifics of the task data structure to implement this algorithm. I mean, it's fine, right? You know, this is a fine way to do it, assuming, you know, whatever issue that caused it to run for 10 seconds is addressed. But really, like when you look at the API of FS2, we really want a way to be able to provide this type of program structure without having to rely on anything specific about the effect type. So how could we do this without relying on a method that's specialized for tasks? Well, we could go back and look at the time package again. So the time package had a sleep operation. So we could say sleep for 5 seconds. Now, just like before, we have to tell it what effect we want to sleep in. So we're going to sleep, and task. And now what we get back is a stream of task and nothing. So I want to kind of unpack this for a minute. First, we're using time.sleep, and I had to tell it that I want to evaluate in the task effect, but I'm not relying on anything specific about task here. This is much different than like calling task.schedule. Right? Task.schedule, that's a method on the task type. It's specialized, right? It only exists on this task data structure. Whereas here, time.sleep is defined polymorphically for every effect type that has this async type class. We'll talk more about the async type class in a future talk. So this is much different, right? This time.sleep pattern is going to work with arbitrary effect types. The next thing to point out is like the output type here is nothing. And just like before, right? Because the output type is nothing, we know that we're never going to see a value. You cannot have an instance of nothing. You cannot have a value of type nothing. So what's the point of this time.sleep constructor? If we were to say just run.UnsafeRun, what happens? You can see we block, and then after 5 seconds, it returns. So this time.sleep ends up being a stream that never outputs anything, but doesn't actually finish until this delay has been reached. So with this combinator, can we construct something that works with interrupt when? Right? Interrupt when doesn't interrupt when is going to require this true value to stop evaluating the other stream. So how can we get a true value after a 5-second delay? And the nice thing is that it's actually very straightforward. You basically just write out what we just said. So we're going to sleep for 5 seconds, and then output a stream with one element true. Right? So if we were to run this stream, we'll have to, since we don't have anything that's showing us the values, we'll just run log for now. It'll wait 5 seconds, and then a true will show up. We've just appended these two streams together. So finally, we can plug this into interrupt when and say sleep for 5 seconds, and then return true. And we still, in this case, have to provide the effect type we want to evaluate in. This is a pretty standard approach, this ticks.interruptWhen, of canceling a running stream-based program. There's a little bit more common overload of interruptWhen, the other method here, that takes this asynchronous signal. And the idea there is that you sort of have like this value in memory somewhere that in some sense is mutable, that eventually will probably change values. And we're going to interrupt our left-hand side stream as soon as this value in memory switches to true. So it sort of sounds a little unsafe, but it turns out it is completely safe and completely referentially transparent. And in fact, this second overload of interrupt when built on signals is actually implemented in terms of the one we just used. So next time when we meet, we will talk about this FS2.async package and look at data structures like signal, as well as some others like queues and semaphores and maybe even topics. So that's the material I wanted to cover today. Does anybody have any questions? All right, thanks everybody.